Hello, welcome back to one more lecture on the fundamentals and biomedical applications of quantum science. Well, in the last lecture, we start to see the so-called two-level approximation for the light-matter interaction. I explained to you that in most of the time, when we consider two levels only, even though matter is much more than two levels, in a few systems, we have real two levels. That makes a lot of the things simplified. And we can, with this, explain to you many of the effects that takes place during the matter-light interaction. So we have then an approach that considers only two levels. The solution of the problem involves, therefore, two wave functions. The two wave functions are psi1, psi2 with the time independence, which is basically the energy of each level, and the spatial part. And we made an approximation for the electromagnetic wave. We made the approximation that the electromagnetic wave has no spatial dependence anymore, only time dependence, because we're dealing this term on the spatial dependence of the electromagnetic radiation is very small, because we are dealing with the size of the atom or the localization of the electron cloud in an atom or molecule, which is angstrom type, multiplied by something that is on the order of at most 10,000 times bigger. And then the product is very small, and that justifies for us to do an approximation where we consider only the time variation. And then the solution for the problem, it is a combination, right? Of first this one here, we discuss the interaction, and in this case, the interaction is a dipole type interaction. Basically, to visualize, you can think that the electromagnetic field is displacing the cloud, making it like another state. And then there is this displacement is equivalent to move the charge, is equivalent to a dipole. And therefore we call dipole interaction the energy. We already discussed the interaction energy. And the solution in this case, is a superposition of the two states, because everything we have in your system is a combination of psi1 and psi2, which are the solutions of the system without interaction, with the coefficients that depend on time, and the coefficients represent the probability of having the system in one of those states. And then I made some consideration about the property of the states, that they are orthogonal and everything, and explain to you that we're going to solve the problem. And that's what we're going to do now. Let's solve this problem. Let's consider the Schrödinger equation, which now is going to determine to us the time evolution of this state, which is a combination of the two. Well, the Schrödinger equation in this case involves a H0, which is basically the system without interaction, plus an energy term, which we call this Hamiltonian term, which is supposed to represent the interaction, in this case, the interaction considering dipole type interaction, as we discussed. The solution is like this, is a superposition of the two states, psi1 and psi2, which is the universe. It's everything that this system can exist in. We cannot have the system in any other state, either one or two, or a superposition that evolves in time. And the whole thing is to determine the coefficients, A1 and A2. Then I just expressed the solution here, psi, which is the overall solution, putting explicitly the two states. We have A1 that depends on time, and we have A2 that depends on time. We have explicitly the time variation of the first state with the spatial variation phi 1, and the time dependent of the contribution of the second state and the spatial dependence of the second state. What we're going to do now is just put this solution in this equation. So when we put here, we're going to have time variation of the coefficients, because phi are not time dependent, so we will not be involved in here. And we have something important. Let me explain to you that when we have H0 in phi 1, this is solution for the state 1. This is just the energy phi 1. And H0 in phi 2 is just the energy of the level 2 phi 2. Because this is, remember, H0 here represents a cup of operation, is the energy of the system without interaction. But it has the kinetic and the potential contribution that determines the system itself without the interaction with the radiation. So taking into account this type of solution, when we plug this solution in here, we're going to have a lot of terms that we know. The only thing that we don't know is how the interaction acting in phi 1 will result. What is involved in this? Remember, the interaction is the dipole interaction, which is basically the variation of the time variation of the electromagnetic field times this dipole. And the dipole is the charge of the electron times the displacement. We live as a dipole element here, and that's well characterized. Let's put the solution in the equation. This is a straightforward thing to do. You know, this guy is time dependent. We're going to have derivative of A1. That the derivative of A1, you know, we call A1 dot. Dot represents the time derivative of either of A1 or A2. So when we put this here, we're going to obtain a couple of, you know, because you see, let me explain that at the end of the day, we're going to have a part that's depending on phi 1 and a part that's dependent on phi 2, but they are orthogonal. So we can multiply and we can have two equations that are independent. One that tell us, so plugging this in there will result two equations. What are the two equations? Exactly, equations that determine how is the time variation of the coefficient A1 and the coefficient A2. Right? And what is this V12? V12 is the integral of the interaction considering the level 1 and 2. V12 is the integral of phi 1 complex conjugate the interaction term. This is H interaction, right? Is this term here. Phi 2. If this guy acting on phi 2 gives nothing, gives phi 2, this is 0. So this coupling is not possible. This interaction do not couple state 1 with the state 2. And V21 is when I start with 1 and end with 2. This does not couple the state 1 to 2. So we have here the two, what we call, this is equivalent to the matrix element that I spoke to you before, but now specifically for the dipole interaction. And here there is the time dependence that is just transparent to everything here because nothing depends on time, so this will come in just in front, right? And then this is the element. So you can see that e to the minus I omega will be here combined with this time dependence in either case, right? And E2 and E1 are the energy levels of the two states. So you see that the time variation of the coefficient A1, for instance, this will be a fast time variation if this is big. So if the couple of state 1 with state 2 is big, then those time variations are fast. If they are small, if they are zero, there is no time variation, there is no coupling. If the system starts in one state, we will die in that state. So you see, we convert the wave function equation, the wave function and the time dependence on it, which is given by those coefficients, we convert in a time variation, in a time equation for the coefficients A1 and A2. And they are coupled. Of course, any student for engineering school can look to this and say, well, take one more derivative. We know that this is not time independent except for the e to the I omega t, which is explicitly. And then I have the derivative of A2 here, and the second derivative of A1, and then I plug A2 here. So if you do this sequence, if you do a sequence like this, we're going to end by solving. I'm going to have a second order time differential equation for A1. We solve for that. And then we will end by having solution for A1 and A2. Okay, so let's do that. But before doing this, I wanted to remind you that I already explained to you that we have a very important condition, which is the conservation of probability. A1 in time square plus A2 in time square is equal to 1. If one grows, the other has to come down, and vice versa. Because the A1 square is the probability of you find the system in state 1, and A2 square is the probability of finding the system in the state 2. And the sum of them, because that's everything that can take place, adds to be 1. Okay, well, we have, I already told you that the dipole is the charge of the electron times the displacement, the coordinate. So that's the dipole interaction. It's a dipole, right? It's the dipole of the electron during this interaction of the electromagnetic field. So you're going to have a dipole that's going to oscillate as well. We're going to now simplify a little bit, removing the time dependence of V12 and V21. Just going to remove the time dependence and put explicitly the time dependence together with the other that we had already on the states. Time dependence, we put all together, the time dependence of the electromagnetic field together with the time dependence of the evolution, natural oscillation of the states. So we're going to name it Me12 and Me21, you know. So the me, which is this Greek letter, will be phi 1 integral of phi 1 dipole element phi 2, and my 21 is phi 2 the dipole element phi 1. That's crucial to understand that for this to work, this is like an operator on this wave function. So whatever this is not zero means that those states that normally are orthogonal, if I remove this is zero, right? We know, I already explained to you that they are orthogonal. They cannot one be projecting the other. So that's zero. But because of the interaction, this state starts to look like this state. So when I act this displacement on this state, it has something that looks like the other, and then the projection is not zero anymore. The dot product, this is like the dot product of this and this modified by this interaction. It's not zero. So that when this is not zero, we say that there is a coupling by dipole between the two states, you know, because one is the other by a displacement like. And if this is strong, this is very strong coupling. If this is weak, it's not so strong coupling. Of course, they are equal in modulus, because if you take the complex conjugate of this, you see that one is the other. So basically they are equal in modulus, and we're going to consider them as equal in modulus because it makes sense here. Okay, so I already explained to you that in this approximation, the two states are coupled by radiation by a displacement of the electronic cloud. Now continues what I promised to you. We're going to put explicitly the time dependence. So the whole time dependence, explicitly time dependence here, is omega. Remember that omega 1, 2 is basically E2 minus E1, which is the true energy. So it's the difference in energy of the true state divided by h bar. So it is the energy difference between the states expressed in frequency. That's what it is, omega 1, 2. And omega is the radiation. This is radiation frequency. And of course, we always like to work with the frequency in angular frequency, because we're going to express functions in terms of that, and then it's easier to work with the angular frequency instead of the 2 pi times the normal frequency. Okay, so the two equations that I had before, which is this one, I put the time out of the integrals, and this term I call mu1, 2, which is the dipole element. So I redefine, so this is now my matrix element for the dipole. So I took the time away. Of course, v1, 2 is just the time, the e to the minus I omega t times the dipole. So the dipole will basically oscillate with, this is basically the induced dipole. This is charge density times E, which is the charge density, right? When I have this, it's like a charge density that it generates by this interaction multiplied by displacement, which is the dipole. So then we put explicitly, so we're going to have here the term, the radiation frequency, adding or subtracting from the frequency representing the energy levels of this two-level system. And then we have the same equation. First derivative in time of A1 depends on A2, and the second derivative, the first derivative of 2 depends on 1. Physically, it's very interesting to understand this, because for the time, for the probability of the state 1 vary, you must have A2 not 0. So that A2 must be receiving population at that moment, probability at that moment, and vice versa. So we have then those equations. Now I'm going to do what I promised you before, which is taking the derivative. I'm going to take the derivative of this, take the time derivative of either. I'm going to take the time derivative of the second one. And here going to appear a A1 dot. I'm going to substitute by this, the A1 dot. And of course, I'm going to use always the fact that A1 square plus A2 square equal to 1. Okay, doing this, we end by having a very nice equation for A2, but we cannot say that this is the wave equation. we already removed the wave from the story. We are now with the coefficients. And the equation that I have to solve is a second order differential equation in time, which solution is going to give me A2. And I know, knowing A2, I know A1. And here there are many things that appear, which is the amplitude of the field. We normally, I call before E0, right? Here I still have epsilon 0, but E0. E0 times the dipole is the energy. We all know that field times dipole is energy, right? So this is the energy of this interaction. And divided by h bar is like expressing this interaction in terms of frequency. And that has a very famous name in frequency. It's called Rabi frequency. Rabi, you know, Rabi, the inventor of the NMR, the very important guy in the formation of the quantum mechanics and the interaction of radiation with matter, he proposed that this interaction, I don't think he gave his name, that came later, but we call this Rabi frequency. So this is a frequency divided by 2 square. You agree? So we have a frequency here, we have a frequency square here. So everything has the right, because probability does not have dimension. So this is 1 time square, now this is 1 time square, and this is 1 time square. And we have this equation, second order equation to solve. This looks like a damped harmonic oscillator to solve it. Here we consider all the interaction present, right? Very good. Well, in doing that, right, so we're going to rename the frequency, the Rabi frequency. We're going to rename the Rabi frequency. So we now that equation on the top, because we call that the Rabi frequency, it became this frequency. And we have this equation to solve together with a constraint, which is the sum of A1 and A2 is 1. So there is a bound to A2 somehow. A2 square cannot be different from 0 to 1, right? Otherwise this does not hold. That's an important constraint we have. Now we're going to solve this equation. When we did the original equation, there is a term that comes with the addition of the frequencies. This term is called the anti-resonant term. I neglect it because they're gonna come with, you know, what be important is the term that has the difference in frequency that we're going to call delta, the detuning. The term that comes with the addition is going to appear in the denominator, and this will go away because this is a so big frequency that zeroes out when compared to terms that. So this is the anti-resonant term, you know, and we neglect it. So when we solve this, when you migrate from here, from this equation, that is this term here, which is going to give origin to this anti-resonant, and you're going to neglect it because at the end of the day, they contribute very little to everything, believe me. So we neglect it, take away, and solve the equation. When we solve the equation, we're going to have to imagine in t equal to 0 some initial conditions. I'm going to say that in t equal to 0, the system is in state 1. So A1 is 1 and A2 is 0 at this time. So this is like considering the equation, you know, because we substitute, we have now an equation for A2 that we're going to solve. And with those constraints, neglecting the anti-resonant term, and with the initial condition, see, I'm not giving all the steps of the calculation. to not use the time, but you can do yourself if you want, and this is present in many books, you know. And there are nice ways to solve this. I solve by the Schrödinger equation, but there is also a nice way to solve the two-level system, which is by the density matrix method, which is wonderful. You know, if you are involved in physics and if you're going to go deep into this, you should do once this solution using the density matrix concepts. Okay, but this is a little one step up from what we want to transfer to you. You have to understand that quantum system, you know, there is a logic on everything I'm telling you, right? The system is a two-level. It can only be in those two. If you put something that varies in time, will promote system to be more in one in the other, probabilistically speaking, and this will depend on time. And this is what we're solving, right? Very good. So, putting all these conditions together, so we have this time-dependent equation, constraint, and now I impose some initial condition. The system will start at the t equal to 0 at the first level. Only t equal to 0 is in the first level. Let's see what's happened here. Well, the solution of this equation, it's clear. Sines and cosines combination, but believe me, when you solve the equation, they will be sine and cosine square. So considering those initial conditions, we can find, I'm not asking you to do in detail for this course, but if you are interested, you should do it, you know, and it is in many, many texts, and you can do, based on everything I give you, you can propose the solution. We get the solution. We get A1 square. I already put A1 square and A2 square because it's easy, right? So A1 square. In the notes, I think I didn't put the square, was a fault. You can correct. And this is A2 square. It's given by those expressions. You can note that A1 square is given by this. When t equal to 0, this term goes away, this term is 1, and that is what I told you that was the initial condition. In t equal to 0 is equal to 1. And A2 in t equal to 0 is 0. So A2 in t equal to 0 is 0. Right? So this is here already. And the A1 has this nice combination of sine and cosine square. And there is this amplitude for sine. And 1 for the cosine. And A2 square, which is very important term based on the conditions, the initial condition we imposed, is omega rab square divided by delta square plus omega rab square. What is delta? Is the so-called detuning. Basically is how far is the photon energy from the difference of energy that I'm going to have to put in the system to promote the transition. And this is called detuning. Very common word used in spectroscopy and everything, and it's called the detuning. If I add up this term plus this term, you can see that the coefficient of the sine square comes to be delta square plus omega square, omega rab square divided by delta square is 1. So at the end, when you add up these two, you're going to have a sine square plus cosine square, which is 1 independent of the time, which is the condition that we impose to this. That's the condition we imposed to the whole system. Right? Okay. Now, let me show you what's happened to, well, of course, I mean, I can put that A1 is 1 minus A2, and if you express A1 as cosine plus sine, you can see directly that knowing A2, you determine A1 exactly. So as you can see, with the definition of the detuning and the verification that this solution obeys this, we can, having A2, which I stress here in red, and I'm going to use this, because why I'm concentrating A2? Because I told you that we start with A1 equal to 1, and A2 is the build-up of the transition from 1 to 2 as the time evolves. And we verify the relation. So we are very good with this. Now I'm going to show to you how is the time evolution in a plot. The time evolution in a plot of what we just observed. So let's imagine that the delta equals to 0. If delta is equals to 0, this is 1, this is 1. So basically, the A2 is a sine square variation. Starts in 0 because this is A2 square, right? A1 is 1 at this point. A2 is starting 0. And as we wait in time, this grows, reach 1, start to come back, goes, start to come back, grows. So it's like the probability starting 0, goes to 1, goes back to 0, goes to 1 again for delta equals to 0. Delta equals to 0 means I'm matching exactly the frequency of the light with the frequency of this two-level system, and that's called full resonance, right? Now, that's very interesting because the electromagnetic field brings the system, brings the probability to be in the other state and then brings back, because of course we are deforming the wave function, the cloud, by displacement, by the R. It looks like the other state, but then nothing happens, it distorts back, comes to 0, which means when it reaches 0 here, means now the probability of the system being state 2 is 0 because this is A2, but the probability of being state 1 now is 1 again. And this oscillate. What is the frequency that this oscillate? For delta equals to 0, this is oscillating with the Rabi frequency. So the Rabi frequency, we have a Rabi frequency line, which is basically the root square of delta square plus the Rabi frequency square, right? So we define this, so it's easy. When delta equals to 0, this here is oscillating with the Rabi frequency. So the oscillation that you see in time is the Rabi frequency. So this is oscillating exactly with the Rabi frequency of this transition. And I already defined the Rabi frequency previously as being the interaction, the energy interaction of the dipole, mu, with the amplitude of the field divided by h bar. So basically is the how strong is the interaction via dipole type approximation. Now, if I change the detuning, so this is no longer 0, but the frequency of the light is a little different from the frequency of the level. So the radiation frequency is either smaller or bigger by some amount that we're going to call delta. I don't care about the sign of delta because the delta always comes square here, you see? Doesn't matter if it is what we call red detuning or blue detuning. Normally when this is positive, we call blue detuning. And when this is negative, so when this is negative, we call red detuning. So let me put the blue plus. That's a notation that the people in spectroscopy use a lot. Blue detuning means the frequency of light is above the frequency characteristic of the levels. And red detuning means below, right? So don't forget that. Now, if we put a detuning, either positive or negative, the oscillation now is different. We'll never reach the 1, so you never have a full probability to be in state 1. Always is smaller, the amplitude is smaller because of this term here. If this is not 0, this guy here is never 1. And this oscillates, reach a value, which you know what value is that, is the Rabi frequency square divided by Rabi line frequency square, which is with the detuning, and this oscillates the same way. The probability oscillates up and down. So the system is like oscillating between the two states, the probability to be found. If I turn on, wait some time, there is a probability to find here, and then that's decrease and so on. Right? And this will oscillate with what frequency? With a frequency square, which is the D1 square plus the Rabi frequency square. That's the frequency of this oscillation in time. Is the modified Rabi frequency. Finally, if I increase the detuning even further, if the frequency of the light and the frequency of my system is different, it's always start to 0, but now oscillates faster because as the detuning increases, it oscillates faster. Much more oscillations per unit of time, but smaller amplitude because now delta is big. When delta is very, very big, this zeroes out. This basically goes to 0. So it's like a tiny, fast oscillation around 0 here. Right? So this oscillation means that the light is producing a coherent superposition of the two states. As you leave the light on, the probability to find the system in either states oscillate in time. Depends when you look, you may find the system in 2, or you may find the system in 1 again, or in any intermediate region. So here is just you're always going to find the system in 1 or 2, but with different probability oscillating in time. So this is very interesting thing, because if I turn on the light, wait time long enough to transfer all the population to the level 2, I end with my system in the level 2. This is the probability for one atom, but if you multiply by the number of atoms you have in your system, you have the population. If you are illuminating all the atoms equally, or if you're illuminating a solution with many molecules, we normally like the probability oscillates in time in a coherent superposition of the two states. That's a very important thing. As I told you, we can transfer population. We can partially transfer population, right? Because we're dealing, as I told you, with the molecules in a system, many of them. This probability, which is a probability, times the number of particles, represents how many particles we expect to be in each state when I make a measurement, right? And we're going to put this in some activity for you to do, some homework for you to testify with this. Okay, so you see, that's a very rich oscillatory system. What we see, like making a summary of things, we observe the following. We observe that when we turn on the radiation, the system oscillates between both states that are possible. What the electromagnetic field does is promote this oscillation of the population or of the probability to be in each of these states. One thing you can never forget is that the system oscillates with a frequency that's called Rabi frequency, and there is a modified Rabi frequency that's depending on the detuning. Interesting, if you are very far from the matching of the resonance, the system oscillates fast, but with very tiny amplitude. Large detuning, therefore, produce faster oscillation, but smaller amplitudes. Right? This is the main thing that we observe in those plots. Large detuning, smaller oscillation, smaller amplitude of oscillation, and faster frequency. So basically, what's happened, if you want to have a picture in terms of the orbitals, the electromagnetic field, the E field of the radiation, because we're dealing with dipole, excite and de-excite the system in a coherent way. So imagine you have a S state. So that's the part I like most, is color. We start with a S state. The electromagnetic fields acts on this S state. Displace the wave function. Promote to go to a P state. And you can imagine that an electrical field will do that. Will try to make the cloud to go that way. But the electromagnetic field is still acting, so makes coming back. And this period of oscillation repeating, right, this is what's happened. It happens in a frequency which is the Rabi frequency. So that happens in the Rabi frequency prime, which is the modified Rabi frequency, because you may be in any detuning you want. The electronic cloud changes characteristics, and that's what we have to have in mind. Well, you may be thinking now, where the energy goes when the field put energy in this? Well, it goes to the electronic cloud, because this is in a superior level of energy. But when it comes from here to here, gives back to the field. So this is a coupled oscillator. The electromagnetic field is like an oscillator, and the atom is another oscillator. It keeps breathing. The energy goes from one to the other. There is a situation that's very interesting. Suppose you have two pendulums of different characteristics, different masses, and they are coupled by a spring with some constant. If I put one to oscillate, you see that the energy migrates slowly to the second and stops the first, and then migrates to the first, stopping the second. The energy migrates here from one pendulum to the other. This is the couplet oscillators. And what we have during the interaction of radiation with the atom is a situation of coupled oscillator. The electromagnetic field is one oscillator, and the matter, the atom, through the atomic orbitals and to the quantum distribution of the charge, is the other oscillator. And they oscillate in time, one another. That's a very interesting situation. And I think I could stop the lecture here, but I still have something else to say to you, but I'm going to do in another part of this lecture, because that's important thing. But we have to keep everything I told you in mind, because this creates to us the intuition to understand how the light interacts with the matter on the semi-classical level. Right? Because we did not quantize the electromagnetic field. We are not dealing photon by photon, but we're dealing with the oscillation. And this is the classical picture. Okay. Well, I think we have one more lecture to go, and I will do that the next time. See you then.